We can compress strings using Huffman encoding. The principles of Huffman encoding is to have higher frequently occurring letters represented by fewer bits and lower frequently occurring letters represented by more bits, thereby maximizing the efficiency of the compression. So in this situation, we are going to apply Huffman encoding to the string Henry Horse, and we're going to work out how much space is saved after we've applied Huffman encoding. The first stage in the process is to create a frequency table. So in this example here of Henry Horse, we have two H's, we have two E's, and we have two R's. All the other characters, we only have one each of those. We also need to consider the space as well. That's also considered a character too. The next step is to order the frequency table. So in this situation, what we've done is we've put the lowest occurring characters at the top, so the low frequency characters at the top, and the higher ones at the bottom in this table. Now we're in a position to begin to create the tree. What I've done here is put each of the characters associated with their number there, the frequency number, in a little box. So the first step now to create this tree is to take the least frequently occurring letters and then begin to combine them. So at the top here we have the least frequency occurring letters, so that's N and Y, and now we've combined them, and then we write down the number of letters that we now have in total, so that's 2. The next stage is to reorder the letters again, because we've got now 2 for the N and the Y, so N and Y now represent 2 characters. We need to place that now in the correct position in the order of those characters. So again, we have the least frequently occurring letter at the top and the highest ones at the bottom. The process then repeats. So we have the least frequency occurring letters at the top. Now we've got S and O, and we combine those, and we have now 2 of those in a new box. Again, we need to reorder according to the frequency of characters. And again, we can continue to combine. In this case now we're combining the space with the S and the O. Now we have 3 characters there. Here we've done some more reordering, and here we are continuing to combine our lowest frequency characters, and we're continuing to do more reordering, more combining, and we're going to keep doing this until we just have a single tree left. Reordering, we have more combining. Now we're left with 2 trees, so we still need to go through the process again one more time. So we've reordered everything for a last time, and now we're combining those last 2 trees to complete our tree. So we have 11 here, and that's exactly the number of characters we have in our string Henry Horse. The next stage is to add ones and zeros to the branches. So where the branch goes down, we add a 1. Where the branch goes up, we add a 0. In step 5, we need to encode the characters. We do this by tracing the path from the root node. So the root node is the rectangle with 11 in, and we follow the path to each of the characters. So let's start with E. So if we follow the path, we go along 0 and then we go 1. So therefore it's encoded as 0, 1. So E is encoded as 0, 1. H, we go 0 and 0, so that's simply 0, 0 for H. R is encoded as 1, 1, 1. Space is encoded as 1, 0, 0, and so on and so forth until you have encoded all of your characters. Notice how the high frequently occurring characters have fewer bits to represent them, and lower occurring characters have more bits to represent. So that's kind of where the efficiency is made with Huffman encoding. So fewer bits to represent high frequency characters, more bits to represent low frequency characters. The final step is to encode the message. What we do here is we find the corresponding encoding to each of the characters. So starting with H, the corresponding encoding for that is 0, 0. For E, it's 0, 1. For N, it's 1, 1, 0, 0. For R, it's 1, 1, 1. And we keep going until we have encoded the entire string. By adding up all the bits, that will tell us the compressed size. So in this case, we have 33 bits. The uncompressed size can be worked out by multiplying the number of characters that we have, which is 11, by the number of bits we have per ASCII character, which we know to be 7. So the uncompressed size is 77 bits. Therefore, we can work out that the compressed size is 44 bits smaller than the uncompressed size.